All right, so in this lesson, we're going to learn some more techniques that'll make our lives a little bit easier, but more importantly will allow us to evaluate more complicated functions using Laplace transforms and inverse Laplace. And rather than derive it, we can use certain properties of it. So let's start with this first property that if we're defining the Laplace transform of lower f of t equal to capital F of s, then if we take that same function times e of at, it's merely a transformation of capital F, s minus a. So how does that work in, say, an example? Well, just a quick reminder about Laplace transform. So let's just take t cubed, for example. So if you go back in your notes, I guess before I do the t cubed, let me do t to the n. So t to the n would be n factorial over s n plus 1. Okay? So t cubed would be 3 factorial over s to the 3 plus 1, which would give us s to the 4th in the denominator, and 3 times 2 times 1, so that's 6 over s to the 4th. Okay, so let's put that with this new property, which says if I take the Laplace transform of e to the 5t times t cubed, that e to the 5t can simply be converted into s minus a, so a in this case would be 5. So that would be 6 over s minus 5 to the 4th power. Okay, so in this next example, let's review the Laplace transform of cosine 4t. Or sorry, I keep forgetting I gotta generalize this. All right, let's look at the kt rule. So that's simply going to be s over s squared plus k squared. So in our case, cosine of 4t would be s up top, and then s squared plus k squared, which is 16. So if we take into account that e to the negative 2t, so let me set that up, e to the negative 2t, cosine 4t. Okay, so essentially takes anywhere I have an s, and there's going to be a subtract a negative 2. Plus 16. So we can kind of clean that up. So that's an s plus 2 in the numerator, and an s plus 2 squared plus 16 in the denominator. And there might be a need to multiply that out, simplify the denominator. I mean, obviously we're going to do more with it, but as far as transformation goes, there we go. We've taken into account what that e to the negative 2 does. Okay, so as you might have guessed, the inverse Laplace is where this gets to be more interesting for us. But if I can essentially get my inverse Laplace to be written in some sort of transformation of s, where it's s minus 3 in the example we have down below, then that would translate into some exponent of e to the at, right? So we're going to utilize that rule to see if we can simplify some of these more complicated Laplace inverse Laplaces. So let's actually look at this first example. So let me scroll up. All right, so my first task here is to actually figure out how to separate it into different fractions because we don't have a squared inverse Laplace. So there's nothing s minus a number squared gets me to convert that. But if I have it in some sort of fraction, so let's focus on that 2s plus 5 over s minus 3 squared. And that's where partial fraction decomposition is going to come out. And so in partial fraction decomp, there is a case where there's a repeated root. And so our fraction is going to look like something. Oh, what happened here? Sorry about that. It's going to look like a over s minus 3 plus b over s minus 3 squared. Okay, so if you remember how partial fraction decomp works, I'm going to put it back over the common denominator and look at what happens to the numerator here. So that'd be a times what's missing, and it's missing a s minus 3, and b is missing absolutely nothing. So that then says that 2s plus 5 equals a times s minus 3 plus b. And then we get to do a little bit of solving. So this is where smart x's are going to be, or smart s's we'll call them, would be helpful. So maybe I want to try s equals 3 and see what that tells me. That should tell me what b equals. So 2 times 3 plus 5. And then the a term gets canceled out when s is equal to 3. So that tells me that b is 11. Okay. So that said, now I just need sort of another useful number. So s minus 3, and I just need to pick something that would be nice to solve for. I don't know, multiplying, oh sorry, not b, 11. We know it's 11 at that point. So it's always nice when I multiply by 1. So what if I let s equal 4? So if I let s equal 4, so it's 2 times 4 plus 5 equals a times 4 minus 3 plus 11. So 2 times 4 is 8 plus 5, which is 13. We'll subtract off that 11. And that's just a, so that tells me that a is 2. Okay, so then come convert that back into our fraction. So our Laplace inverse is going to be 2 over s minus 3 plus Laplace inverse of 11 over s minus 3 squared. And I can bring those, the 2 and 11s out. So that's 1 over s minus 3 plus 11, 1 over s minus 3 squared. Okay, so then we want to look back at our chart and we want to see, okay, which inverse Laplace from lesson 7.2 fits the closest to what our pattern is. So I'll just kind of remind us, because we actually just saw this in the previous example. So n factorial over s to the n plus 1. And keep in mind, we can ignore that minus 3 because that minus 3 tells us it's transformation of e to the at. So that would be t to the n. Okay, so that's the one we're going to use in this case. So 2, and then what would our be 2e to the 3t plus 11 e to the 3t times t. And there we go.